Okay, so today's video is going to be about uh, the two operators of the quantum mechanics, the two main operators of quantum mechanics. Again, quantum mechanics. So, the main topic I will be discussing about is the ladder operators. Operators. What I mean by ladder operators is if I take them into two parts. One is creation operator, other one is annihilation operator. Now we will know about the reason behind why they are known as the creation and annihilation operator. But before we talk about them, we need to study one more topic, SHO, simple harmonic operator. So simple harmonic oscillator operator, no operator, no, oscillation, sorry, oscillation, simple harmonic oscillator or oscillator. Okay, so simple harmonic oscillator has two. It is defined in classical physics plus our main topic, quantum physics, quantum mechanics. But first of all, in classical physics, how does simple harmonic oscillator work? We can know by the word oscillator, it means it's moving within a range. So the best example of simple harmonic oscillator is this. Okay, so this is a mass m, and it's tied to a spring. This is a spring. Okay, so what we are studying is if this is its equilibrium point. So when we apply force on this mass connected to a spring in this direction, okay, when we apply force, when we push it to this direction, when we move it x, not apply force, we will move it to from its equilibrium position by x. What will happen is that the force which is being applied will be opposite to x. It will be in the opposite direction, and then if you leave it, it will oscillate back and forth until it will come back to its original position. So we can say the force is directly proportional to x or negative x. Because of it, they're opposite sides. When we move this mass position x from its original position or equilibrium point, it will have a resistive force. This force is opposing force. So now we will make a potential energy. This is what the main point of simple harmonic oscillator. A spring which is a mass connected to a spring which is moving back and forth has potential difference in terms of spring, not height. So here what will be the equation? It will be 1 by 2 f x square. Now fx square here is very interesting because we know that minus x is our distance moved, as I assume this minus x as force is negative. Even if I write it like fx, we still have negative, so it doesn't change anything. So here we have a very interesting thing. When we put x square, because we know that minus x assumes that as any value, it can be any value which is negative, but x square even if it's negative, positive, whatever the value is, it will always give us a positive value, because anything in the bracket square will give us positive value. So, and we know that the graph of quadratic of this formula 1 by 2 fx square will be like this. It will be a curve. Here we only have one turning point, and that turning point is origin. Origin is turning point. Turning point. And the object, that mass is oscillating here. Oscillation of mass. Oscillation of mass connected to spring. Okay, so this is how the mass will move up, down, and in motion. So now that we know about this is P dot E, or if I write it in exact, elastic potential, no, potential difference of spring, or yeah, in terms of spring. Okay, now that we know about the oscillation of oscillation in classical physics, let's move on to our oscillation in quantum mechanics. It's known as quantum simple harmonic oscillator. Okay, so now that we will be talking about quantum simple harmonic oscillator, it's actually very hard to find a quantum simple harmonic oscillator. It's not that easy to find it in terms, because if this is at macro level, we for quantum simple harmonic oscillator, you know what will be the thing? It will be just like same thing but shrinked. Same thing but shrinked. That's the thing. It's very small. But we can find something related to quantum simple harmonic oscillator. What? Let's suppose if we have we have many ions. Ions are these ions, plus 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 plus, and then it has electrons around it. What are these called? These are called sea of electrons. And when we try to measure the oscillation of these electrons with respect to the ions, ions near it, we will look at like this. And our oscillation is over here. The oscillation we are looking at, this will be our oscillation point of interest. Oh wow, I added something from debate. Point of interest our point of interest in terms of physics, quantum mechanics. So this will be our oscillation. Okay, now if I zoom into this part, this is what I will look at. This is the well. This is known as a well. Okay, but here we will be looking at one of the key points of quantum mechanics. In quantum mechanics, energy levels given to the electrons going back and forth is discrete. Energy level. Okay, electrons is here. It's going up, down, and up, down, and depending on whatever it's gaining or absorbing or emitting electron energy, for which is photon. Discrete. Let me write the key point. Discrete. Sorry. The point. Wait, where is it? So, discrete. Okay, so yeah, wait, let me change something over here so I can have a better understanding. Template settings, grid, color change to this, and yeah, that's good. Isn't that interesting? Yeah. Okay, now I will zoom into this part. I will add one more thing over here. Same, let me draw the same thing over here, but I will be adding one thing here, the wave function here. Okay, one more thing, these are all assumptions. I'm not actually making them according to what I know. It's all assumption. I just want to teach something here. We need to learn because of key point. Okay, now here, let's suppose if I take this point, this one, I zoom in this line and this. Okay, let me just make it more clear, this, so that it's better to understand. Wait, sorry. Now if I take the square of this wave function, wait, let me write this, uh, wave function, it's time dependent, this is wave function. If I take the square of this wave function, what do we get? We get the original position of finding electron. It will, so this shows the electron, or if I make the graph for it, okay, now so this shows that finding electron here, here and here is high probability rather than here. Or wait, if I write it in terms of in this over here, it will be like this, and here less prob. Okay, so now you will be wondering, where is the ladder operator and why is it ladder operator, which is creation and annihilation operator. It's hidden here. How is it hidden here? Did you notice the part when we said about electron rising or coming down of the energy level? Yes, here is the key point. This is energy operator creation. I think I'm wrong with the symbol, I'm not sure, but one is the creation and one is the annihilation. So this is known as a dagger, annihilation dagger and annihilation without dagger, creation. So when it's increasing, when it's going up, it's actually creating energy. So energy annihilation plus wavelength. This is why I told about wave function first. This will give the electron to rise in level. Rise in level. Okay, so now opposite of this is annihilation. This is creation, this is annihilation. Then this annihilation is what? Electron, oh wait, let me check. Electron coming down, which is annihilation. But how does it go up and down? How does it go up and down? It's done by photon energy. Photon is what? Energy. Photon. Here the difference is it's emitted. Photon is, this is emission of photon, this is absorption of photon. Okay, now what else do we talk about? Yeah, okay, let's suppose the ladder operators were not there. How would we solve it? It would be very hard. How? Not hard. It would be, then we would have to use something known as Schrödinger equation. We will have to use Schrödinger equation. Schrödinger equation. Okay. I'll not make the whole equation because I have already made a video on it. I will only focus on one thing. Here I will be talking about the equation itself. I'll just focus on the equation. H operator, Hamiltonian operator is equal to energy operator. So the wave function in this will help us find the probability of finding the electron. But when we use the dagger operator, okay, one more thing, when we integrate, look, we already know about, we already have the potential potential energy, right? So we know that h bar square over 2m d square over dx square psi of x and t plus v of x, no, minus v of x, not plus, minus v of x and t. This can be replaced, in which mostly I said it's constant. This can be now replaced as 1 by 2 m omega 2 x square. Okay. Now I think omega is what was omega about? I think omega is this 2 k over m. Okay. And in terms of quantum mechanics, it would be like this: 2k over or 2m over pi h bar. This I think it was, I don't remember correctly, but this should be what it is. Okay, but we'll not go into details. Okay, let's focus on this. Okay, now what else are we going to? Okay, yeah. So this is why annihilation and creation operators were made. Benefit. Now let me just go to the summary or the conclusion. Benefit of a dagger, which is annihilation and annihilation and creation operator, which are also combined into known as ladder operator, because we go up and down like a ladder. So first benefit makes one more thing. If we have a dagger h something wave function 1 2 3 4 so on x and t, it will give us the position of n psi of x, the quanta, the energy level of the quanta level of the how many quanta levels it were, 1 2 3 1 2 3, okay, and so on. If let's suppose we have n means any number, and energy operator, and this will give us the values. Okay, psi of, I think it should be psi of x and t. They can be multiple, they can be many energy quanta, and in physics and quantum mechanics, when we talk about this, we will be talking the incoming ray, which is photon, as quantum, not photon, quantum. So makes easy calculation. Second point, Schrödinger equation is difficult to solve. Not difficult. If we have another scenario, then why not use that if it's easy and takes less time. Difficult to solve. I think this is the only 2 points I find right over here. So, but still, even Schrödinger equation will, which is not one of the key points. It is the running equation in quantum mechanics. This is this equation down here. I will write here Well, I think I wrote it, yeah, over here. This equation over here is the equation which governs the quantum mechanics world. So, sorry, pardon. So, let's, what else did we talk about? Yeah, let me just focus on the energy or the wave function square. Actually, wave function square over here, let me just take wave function square. Wave function square in terms of, okay, let's suppose if I have this wave. Wait, let me just make a simple wave. I have this wave and I have another wave same like this. Square means when we combine them, we get what? A wave function which is bigger in amplitude. The amplitude over here is A. Amplitude over here is A. Or in let me use. I want to be a quantum mechanics engineer, quantum optics engineer, so I will use the symbols. Okay. So what do we get over here? Wait, sorry. What do we get over here? A double amplitude. So amplitude in these two, single constructive amplitude. Constructive means they combine. Destructive means they will cancel each other out and we'll get a straight line. Resultant 2 pi psi of x and t square. Sorry, I was just okay. So result of psi of x and t. Xt means time dependent. X and time and position dependent. This is what where I and t d over d t d over dt of psi of x and t equal, I think I add this over here. I did, yes. H bar over 2m and so on. I'll not write it again, it will take a long time. This gives the result of our wave functions, and again our purpose here again or here is to find purpose is to find x. You all know x, delta x means position of E minus or particle. E minus would be specified. Okay, and yeah, thank you.